Here we'll quickly demonstrate how we can make use of the MS Excel software in demonstrating multicollinearity problem and also doing some analysis. Blood pressure as our independent variable, as our dependent variable rather, which is y, and age as our independent variable, weight also as our independent variable, the duration of the high blood pressure as the independent variable, pulse as our independent variable, and also stress as our independent variable. You could see that we are having 1, 2, 3, 4, 5 independent variable for this particular work. So what do we do? To start with, we'll first have to use the software to analyze the regression model. So we come to data here, we click on data, you come to data analysis here. Then from this you look for regression. So this is regression. You click on OK here. Then here comes this dialog box. This is where we have to input our y, and this is our y. You pick it from the label to the last value. Then you come here to select input x, which is the independent variable. You also select all the independent variable. You click on label because we are interested in how this labeling to shows in the result we are going to be given. We are also interested in the confidence interval. So there are other varieties of statistics which you might be interested in your own. You can click on them, but we'll be okay with what we have selected so far. You can also determine where you want your result to be post or to be output. If you want the output on the same page, you just click where you have it, but I would prefer we have it on a new worksheet. So I click on this and I click OK to give the result. So this is the result in a new page. So let's look at the result. Alright, so let's look at our R squared. Our R squared here is 0.994, which approximately we could put at 0.99. It's quite a very impressive result, which this is trying to tell us that our model can explain the 99% of what is happening in Y. So let's look at the analysis of variance table. This is the regression sum of square. The regression sum of square is 556.89, and the total sum of square is 560. You can find that the total sum of square total is 560, and our regression model could be able to cater for 556.89. That's quite huge. So we only have just 3 out of 560 that our model cannot say anything about. So we can say that the model also is showing to be significant. The model is statistically significant. This is a very good result, which is suggesting from the outlook of the result initially that each of the independent variables we use in our model, they are useful, and that's why we're able to have up a high R squared, a very huge sum of square regression. But let's now check the test statistics, which will tell us how the individual independent variable is doing. So let's look at age. For age, we have relatively quite small standard error, but more interested in is a statistical significance of the age. So we can find that the age is statistically significant. Let's look at weight. Weight is also statistically significant. Let's look at duration. Duration is not significant, is not statistically significant. Let's look at pause. Pause coefficient is giving us a negative value. So note that, we're still going to come to that. Let's look at the p-value. The p-value is also telling that it is not statistically significant. Let's look at stress. Stress also is not statistically significant. So we have two independent variables not statistically significant here, the stress and duration. But most importantly, this negative value of pause here, let's see how true it's supposed to be. How do we go about that? Let's just quickly have our matrix, our correlation matrix, and see the relationship between each independent variable and the dependent variable. So just as the same way we did, you go to your data analysis, this will come up, you click on correlation, you click OK, then you input your data. So let's have it here. We input all of the data. So, and let's label the first row. So this is the result. I would like to bring the result closer to where I could. All right, so let's look at the correlation between these variables. With age and blood pressure, there's a positive correlation. Weight and blood pressure, there's a positive correlation which is very high. Duration, there's a positive correlation but very weak. For pulse, it has a positive correlation, and it also is a strong one. 0.7 is strong, not very strong, but is strong. So let's check, and you could recall when pulse and BP is having a positive correlation 0.7, it's simply just to let us know that increase in this pulse must be increase in the blood pressure. But see what we have here. This coefficient is negative. So in our model, it's suggesting that pulse is actually reducing blood pressure as they increase. But that's not true. So this is when we have a bizarre beta weight. This is a contradiction. It's a contradiction. Positive correlation between pulse and BP, and here the coefficient is giving us negative. This is a contradiction, and if you recall, that's one of the symptoms of multicollinearity. And also look at some of the individual independent variables, such as we have stress, it's not statistically significant. Also look at pulse, it's not statistically significant, and also duration. You can see we have just 5 independent variables, and 2 out of the 5 are not statistically significant. 2 out of 5, and here we are having a very large R-square value. So this is something that we need to probe further. So how do we probe further? We'll be interested in conducting variance inflicted factor on each of the independent variables. And if you recall, as we have been told in the slide, for us to get the variance inflicted factor of each of the independent variables, we have to, if we are interested for age, given age first, our age here, we are going to be seeing this age as a y, where we treat weight, body surface area, duration, pulse, and stress. We are going to treat them as our independent variable. So when we do that, the same way we go about the analysis initially, this is what we are going to do. Just click on data analysis, look for regression, click OK. Right now this is going to be treated as y, and for the x we have the remaining independent variables. So other things as it were, then we have the new result. So what we'll be interested in this case is just the house squared. As you can see, the house square is 0.432723. so that particular r square is what we're going to substitute into the formula for variance inflated factor, which is simply 1 divided by 1 divided by the r square of the questionable independent variable. And what do we have as the r square? It is here, 0.432. So by just doing this, we get the VIF for h. So as we can see, for h, the variance inflated factor for h is 1.7. Approximately we call it 2. So if we want to talk about h, probably we just say h is just 1 times larger than what is variance is expected to be. But we can see that this is actually so small, we can asymptotically still call this 1. It's not that large, so it is negligible. So as far as h is concerned, we can say that h is not affected by multicollinearity. It's not the variable that is bringing much of the collinearity. So we proceed and check for the other ones. So now we have weight. The weight now stands as our y in quote, while we have the remaining. When you follow the same process as we have done, you have the house square to be 0.8, and in calculating the VIF, which is just saying 1 divided by 1 minus the house square you got for using weight as your y, which is 0.88. At the time you have that calculation, you are going to have 8.47. This is a little bit large. That means we are saying that for weight, the variance for the coefficient of weight is 8 times larger than what is expected to be. I think 8 is quite a large number, but if you recall the discussion in the slide, we said whenever is more than 10, it shows that there is a serious multicollinearity, but when it's close to 1, it shows that it's not something to be worried about. But in this case, our VIF is 8. 8 is not too far from 10, so at least we can still say there's a good measure of multicollinearity as far as weight is concerned. So the next is the body surface area. If we check the multicollinearity for this, doing the same process as explained earlier, the VIF when you use body surface area is 5, which is suggesting that for the coefficient of body surface area, the variance of the coefficient is 5 times inflated than what is expected to be. So let's just quickly look at the remaining. For duration is as close to 1. There's no serious multicollinearity. For pause is 4 times, has its variance to be 4 times inflated than what is expected to be. So I think there should be one more to this side. So for stress is 1.8. we can say is twice more than what is expected to be, and we can also see that one as almost as close as to 1. Alright, so having gotten all this, we might want to check our slide to see those results. Okay, these are the results we have discussed earlier. These are also the results. So these are the variance inflated factor. This is for the age, this is for the pulse, this is for the weight, this is for the stride, body surface area, and this is for duration. We can see basically where we need more attention is in the body surface area 5.38, the weight 8.4, and also the pulse. And if you recall that if you check this independent variable weight and body surface area, there seems to be a related factor, because when you are talking about body surface area and weight, they are almost measuring the same thing. What would be a proof? Let's look at the correlation between weight and body surface area. Body surface area, and this is 0.875. This is large. This is large. There's a strong correlation between weight and body surface area, and for us to be able to have a very good regression analysis and inference, there will be need for us to drop either weight or body surface area. And as a researcher, the choice of what to drop depend on your interest of study and also some other factor. For example, probably in getting my data or in measurement of my data, it is easier for me to measure weight than body surface area, and I think weight is easier in measurement, so probably I will still leave weight in my model where I will drop body surface area. There will be need to drop one of these two. So let's see that. So the VIF value are fairly large. For instance, for 8.42, which is weight, the coefficient has its variance inflated 8 times than what is supposed to be. So let's make some discussion on some of these results that we have gotten earlier. The VIF for weight indicates estimated coefficient of weight is inflated by 8.4 because weight is highly correlated with at least one of the other predictor in the model. Let's look at that to confirm this. Let's look at this. Weight is correlated with age. Weight, let's look at it, is correlated with the age, and body surface area. Okay, weight is correlated with age, and let's look at it this way. Weight is correlated with the body surface area. It's also correlated with pulse. So you can see we are having issue with weight. This is multicollinearity. Weight is correlated with the body surface area. Weight is correlated with pulse. So let's assume we are dropping body surface area. So we're now having weight being correlated with pulse. So let's go down. So weight is highly correlated with at least one of the other predictor in the model. So that's showing where we are having problem of multicollinearity. Also, the variance inflated factor for pulse indicates the estimated coefficient of the exponential coefficient of pulse is inflated by 4.42 times higher. So to remove one of the correlated independent variable is suggested. So there is need for us to remove. We've already suggested removing body surface area. So body surface area and weight is marginally correlated also. We can choose to remove one of them since theoretically they are both similar factors. So we've suggested removing body surface area, and also the choice of one or two to remove depend on the researcher choice, as was said earlier. Say which of the variable is most interest, easily and available and measurable. Also, from the correlation matrix, pause seems to be fairly correlated with age, weight and stress. We may consider removing the predictor pause. So let's look at the correlation matrix we are talking about. So let's look at pause. Pause is correlated with age, is correlated with weight, is correlated also with body surface area, and correlated also with what? Duration. Most importantly is having the highest correlation with age and weight. So there are two variables here that has been suggested to be removed. Body surface area is suggested to be removed, and also pause. So let's look at what we have now. So let's look at the new model we have. We've removed body surface area and we have removed pause. So when we have the analysis, let's look at our R square. Our R square is still 0.999. So which is not different from when we have when body surface area and pause was there, which shows that body surface area and pause, they are providing redundant information about y. They are useless, they are redundant. So despite even removing them from our model, we can see that our R square we still have the 0.999. So we seem not to have lost much by dropping these two variables. So let's look at our ANOVA. Still looking at our ANOVA, so our model can still explain 555 out of the 560 total sum of regression. Initially we are having 32. There's a little bit increase in the residual here, just very minute. We are having 3 point something, now we are having 4.5. So we still have a very huge sum of square regression, and still our model is still statistically significant. Let's look at the individual independent variable after we have removed the ones that are redundant and they are causing multicollinearity. We have our age is still significant, weight is significant, duration though not significant, but they are having a very good contribution to the model. So what do we have here? Sorry, the resulting variance inflicted factor, we are having 1.47, 1.23, 1.20 and 1.24. That means the variance inflicted factor after we have removed body surface area and also we have removed pause, we have to check the variance inflicted factor again. So it's now fine for age. All our variance inflicted factor at this point, they are closer to 1, so we have nothing to worry about, and our R squared value is still very large, and our model in general is statistically significant as we have before. So what we have been able to do successfully is by the variance inflicted factor to have able to check at the models, at the independent variables, whose coefficient and whose are the causes of multicollinearity, and having removed them, we have our analysis, and the result of analysis is as good as what we have before removing these two independent variables. So I believe you have learned one or two things to what we have done in the class earlier before this, so you can check some of this material here for the reference for the work. So I wish you the very best. Thank you.